Hello again, and thank you for joining this webinar on the massive storage engine option as part of our Varnish Plus offerings for a Varnish Cache product. Today we will be talking about the massive storage engine version 3, which is a new product or a new version of an existing product that we are in the final stages of developing and are eager to get out of the development labs and onto servers. Quick words about who I am. My name is Martin Blix Grydeland. I've been a Varnish software employee since 2010 and been the principal developer on these storage features of our product. So let's jump straight into it. Going to start with a bit of history on this product. It's been something we've offering for quite some time. This is major version 3 that we are preparing for releasing. First version was released in 2014, and the goal was to create robust solutions for using caches that are actually larger than the system memory. And make efficient use of disks as an extension of the system memory while still making Varnish perform. So we had a goal of offering multi-terabyte caching, large caches. Specifically, use cases are when latency to your backend servers are high, and you want to offer the disk as an ultimate way of getting content rather than always having to go to the backend for content that could not fit in the cache. This version 1 employed used the technology of the Linux kernel that's called the memory mapped file, in order to extend this address space and create this larger than the system memory cache. So what that really means is that we take the disk and we present it to the application, Varnish Cache application, as a large virtual address space, and then push it down to the kernel in order to really determine what parts of that large file should be in system memory at any given point in time. Which is a kind of quick way of getting that ability without having to go to lengths. And for a lot of use cases, this is a very efficient way of doing that kind of tricks. Another feature or a big part of that product was the fragmentation avoidance, because these caches, of course, they run for a long time, and it's not necessarily that even with the large cache that all your content would fit in. So over time there is also objects being removed and new objects added into the same address space, and over time this has a high tendency to fragment, meaning your performance lowers over time. So fragmentation avoidance was a large part of this. But when it came to the I/O handling and all the bits regarding the handling of the disk, that was pushed out to the kernel. In 2016, we came out with version 2 of this, and here we wanted to add persistence to the cache, meaning that upon restarts, the objects that were present in the cache before the stop would be there also after Varnish was restarted. This, of course, for the planned restarts in terms of software upgrades or the operating system upgrades, but also unplanned restarts like your occasional power failure, or dare I say problems with the Varnish restarting by itself. So this brought with it a couple of new things to make work. We suddenly had a lot of metadata that needed to be persisted. Previously, this had all been in-memory data structures, but now you had the added complexity of getting all of your metadata as well on disk. And metadata in this case is things like which objects are persisted on disk and where on that disk is that object located, so that one could start serving these objects after the software had restarted. And just as importantly, transaction consistency. We didn't want to start serving half of a fetched object in the thought that, oh yeah, we have this object already, this is safe for delivery. So transactions had to be there both for new objects coming into the cache, but also when it came to cache invalidation. So purges or bans being executed should then happen as part of a transaction, and upon a restart you would have to make sure that those purged objects did not magically reappear in the cache. Again, we went with the same type of I/O architecture on the version 2. So it was still a memory mapped file, and all of the I/O handling was pushed out to the kernel. I just remembered there was one point I was supposed to say in the introduction to this that I skipped over. Questions. We are very happy to have questions during this webinar. Questions will be answered in a section at the end, but you are free to write your questions and post your questions at any time, and you can do so in the interface, and at the end of the session we will be going through the questions and answer them in turn. Right, back to the history, or the near future, I guess we are at now, with version 3 of the massive storage engine. Evolution, a bit bold title maybe, but still. Having this product, we wanted to see, okay, it works. It's a quite stable product that does the tasks that we set out to, but there are things that can be improved. And one item that we really wanted to look into is disk utilization. So one of the things we have observed by using the memory map for I/O is that the tasks, the I/O tasks that the kernel sends to the storage device, the disk, tends to be very short. So you end up with a high number of I/O operations for short buffers, and the buffers in this case typically tend to be 4K because that is the size of the pages, the smallest page size that the typical x86 architecture allows for, and specifically the Linux kernel is unable to use any other page size for things that are in the page cache. And the page cache in this case is what the area of memory from the kernel where the data that is being kept in system memory at any given point in time resides. That's where the data that is for high fast delivery option resides, and the page cache is then filled from disk whenever you hit memory that isn't or parts of the virtual address space that isn't present at the given time. So high number of I/O operations, but not enough throughput as a result, because the disks, they have their own limits in terms of how many of these operations they can actually pass through and execute. So even the fast disks, we couldn't feed it fully to its performance because there were too many operations instead of larger operations that would have given a higher throughput. Another point to improve on is the startup time. The way we handle metadata in the MSE version 2 with regards to the persistence part causes quite a lot of I/O during startup because there are some fairly large chunks of data that needs to be copied around in order to create this shadow copy buffer setup we used in order to generate transactions and making sure that it was only whole and complete transactions of data that we looked at, and not be in the situation where a purged object magically reappeared after startup. So startup time improvements were looked at, and another point of improvements is transparency. So this design of using the memory map file and pushing all of the data handling down to the kernel also makes it the kernel quite a big black box in terms of what is actually happening. How much data are you pulling and pushing to disk at any given point in time? We didn't have any way of showing this. We didn't have any way of reacting to it from within Varnish. It was possible to use operating system level utilities in order to see what kind of I/O the system was doing, but you could not see it in relation to what was happening inside Varnish. And we also ran into another kind of interesting limitation to the way of using memory mapped files. In today's world of 64-bit CPUs, we tend to think that address spaces, they are limitless. 64-bit is enough for absolutely anything, even counting the number of atoms in the universe. But we actually ran out of address space, and the limit for this it turns out to be that current generation CPUs they do not actually use 64-bit of address space for their addressing. They use 48 bits of addressing. Even though the instruction set supports 64 bits and is very future compatible with upgrades, current generation only uses 48. And half of that is reserved for kernel space, meaning it is 2 to the power of 47 that actually is the limit of the address space for any given process running on the kernels. So this then also limited our maximum cache size to 128 terabytes, and that also became a limit for some users. So all in all, this led us to reconsider the architecture of actually using the page cache of the kernel through memory mapped files and opt for a new implementation in this area. So in the new version, we are implementing our own page cache solution in user space inside of the Varnish process, using asynchronous I/O as the kernel interface in order to drive the actual disk, but all of the scheduling of the I/O and all of the buffer handling and such is then taken up by the application or Varnish. So looking a bit on the architecture, these slides are kind of simplified, not going into too much of detail, but still showing some differences in the way this works that are interesting. So Varnish, of course, is a type of proxy server. HTTP proxy, you have your client connections coming from the internet. It passes through a server that then is able to inspect and look at what's happening on this type of HTTP request. But if this was a very simple proxy server, of course, everything then goes to a real server that is the actual server of content. But putting a Varnish proxy into the mix, we can then get this image of how we have a cache in the middle. And your connections will then, or the requests will then either be cache misses or cache hits if that was content that Varnish already held. Of course, for the misses, Varnish will keep a copy of this, and the next time someone asks for the very same resource, we will be able to serve that as a cache hit, and doing so directly from system memory. This setup here is sort of your vanilla type of Varnish configuration. It uses the malloc stevedore, it says on the top there. First, a couple of words about the term stevedore. Varnish has a configurable concept of stevedores, where a stevedore is something that handles the object database, the list of objects that we have and where those objects reside for fast delivery to the clients during request handling. So the malloc stevedore is a very simple, straightforward stevedore that just uses system memory. It uses a system memory allocator in order to reserve chunks of buffers to hold the payload data of the objects. And most setups of Varnish will then be using this type of malloc stevedore to just set aside a large chunk of system memory and serve cache hits from that memory. When we made the change to using a memory mapped file, as we do in both MSE version 1 and 2. Then instead of the system memory, we switch this off for the memory mapped file. And the memory mapped file can then be many, many times larger than the system memory. And from Varnish's point of view, it just is a much larger address space. But from the kernel's point of view, it then is tasked with keeping parts of that large file in memory, depending on usage. So the parts of the file that is often referenced should be kept in memory, while the parts that are not referenced should be thrown out in order to make space for other parts. And then shifting client traffic and such, of course, makes this a very dynamic picture. But in the end, the parts that are most relevant should be kept in the file. This is no easy task for the kernel, actually, and the way this type of setup works is sort of, it plays to the limitations of the hardware it is running on. And of course, the implementation in the Linux kernel is a very generic implementation that needs to perform well for most use cases without specializing on anyone in particular. And also the data gathering of information about what parts of this memory is sort of expensive in the terms of a page cache implementation. For the kernel to know what parts of memory is actually being accessed, it needs to resort to some tricks. It needs to set some specific flags on the data structures that define the whole system memory in order to be able to gather data. And it does this by using this page fault mechanism. So it will push out this specific flag on parts of the system memory, which will then in turn cause a trap upon access, and then upon access it can update and say, yes, this is memory that is accessed, and might very well be in the near future as well. So this I shouldn't throw out. But then, of course, it needs to find some other part of memory that is eligible for pushing out. So it will then try to set a flag on some other page, and then again some other page. And it, in practical terms, it ends up always setting this specific flag on approximately half of the memory dedicated to the page cache. And from application point of view, this has the cost of generating page faults. Like, these are soft page faults, so they are not page faults that causes direct disk I/O and reading from disk and long delays, but they are still page faults that happen, and the process is trapped back into kernel space so that the kernel can update its list of what pages are actively being used or not. So this page fault handling, of course, also has some cost to it that comes from this type of design. So going to what this looks like for MSE version 3, we can then see that we are back to using regular system memory or application allocated memory from the pool of system memory, but then adding the disk layer as a secondary layer. So what we really implement here is a type of two-level cache system, where we have a system memory that is very much like the normal malloc stevedore that we started looking at, and how that works. So we are for the top part of this, we are back to the sort of gold standard, what you would use if you're benchmarking Varnish and not try to add any specific large caches or something, but just benchmark in the Varnish itself. That's your typical setup. You use the malloc stevedore because that's the one with the least amount of overhead. So the top half of that is very, very similar to the normal malloc case. But then we add the large disk layer that is where the majority of the content will lie. And we have then a secondary cache where we keep the parts of data, the objects that are frequently referenced in system memory, and the parts that are not frequently used on disk for access by reading from disk when necessary. In this setup, for many purposes, this is the same that was happening in the memory mapped file, but now that we are doing it in user space and inside of the Varnish server, we are able to take notion of to make decisions based off of information that the kernel cannot know. We know the size of the object. We know what the boundaries are for the buffers that are going to be used. The kernel cannot know that and thus cannot take them into account. But we can, in this setup, then make specific choices that are based off of the knowledge of what the application is going to be doing with this data in the near future. So the I/O mechanism is in a special mode of operation that most I/O access in the normal use of files in on a server isn't done in this way. But we use something called direct I/O, and it's a special mode of opening files. And what that does is to really disable the operating system's page cache completely. When I/O is done using direct I/O, it is the user space buffer that is both the source and destination of all I/O operations. So the page cache from kernel's point of view is not in the loop any longer, and all disk reads and writes happen directly from Varnish's user space buffers, which are the very same buffers that will be used for deliveries. So all in all, we then limit a lot of overhead in terms of memory usage. We will get transparency in all stages. It is much easier to reason and know exactly what type of I/O operations that was performed and count these, and we can show performance graphs that then takes these steps that were previously completely hidden into account. Larger chunks gives more disk throughput. We talked about that previously. We should get a better hit rate when we think of the middle layer of the cache there, the fast layer, the one using system memory for caching. We can use a much more stricter LRU instead of the guessing work the kernel had to do in order to set some flags and see what happened. We actually know what objects are being referenced and what is the most valuable pieces to keep in memory. Asynchronous I/O in the picture here is the actual execution queuing of the I/O operations to the disk devices themselves. So it is a mechanism where you can deliver lists of tasks to be performed by the kernel and then get a notification when those executions are finished. So we don't add a lot of threads and specific execution CPU for the I/O operation themselves. All of that still lives in kernel space. And lastly, there is one fairly significant overhead saving that comes from this, and that is the page table entry data structures themselves that are no longer necessary. And all of that comes from the way a memory mapped file needs to behave, where quite substantial data structures are set up by the kernel in order to get the hardware, the CPU, to treat memory in that specific way, where part of it is on disk and part of it is not. And those PTE data structures for very large caches can be quite substantial and eat up a fair chunk of system memory that we will save in this setup. Couple of details about the implementation that wasn't shown on the architecture slides. We have opted to use LMDB in order to keep our metadata. The metadata in this case is the information about what objects are in the persisted store on disk and where on disk those specific parts of objects are positioned as the translation tables in order to be able to read data back in from disk. LMDB comes from the Open LDAP project and is a very fast embedded type of database. And that seems to be doing the trick very well and makes it a lot easier than to handle than the previous metadata solution from MSE version 2, where we had our home cooked setup using shadow copies of everything, and everything had to be copied twice. The LMDB is much more clever in this space and enable to create the transactional part of updates with minimal cost. There are some data journals that also run on top of that again in order to keep updates to the database down, so that we can journal operations that only change simple flags, things like set the flag that an object is already deleted without having to do a full database transaction for all updates. So we can then keep a running journal, and when the next database transaction is run anyways, we can then also update things from the journal. So these data structures is collectively what we in the massive storage engine lingo called the book. So we differentiate between the book that is for metadata in order to keep the persisted part of the cache itself running, and the store that is the actual data object payloads where the actual cached objects reside. When it comes to the object handling inside of Varnish, there are some changes as well that are interesting to look at. So started with a sort of simple diagram showing how an object and the different parts of an object is actually stored in Varnish. And this is what it looks like for all previous stevedores. That goes for the built-in regular malloc and file type of stevedores, and it also goes for both previous versions of the massive storage engine. And there's of course the body part that we can all relate to, and that is the actual body bytes that are part of an object. Consists of a linked list of chunks of some size, and when doing object delivery, of course, we just iterate over that chunk list, and all of this data then gets sent out of the network socket. But there is another part of the object, and that's called the attributes. The attributes are extra sets of data that also belongs to the object, the majority of which will be the object headers. So all of the object headers, all of the extra data, metadata, if you will, of the object that was received from the backend and or created during VCL execution, gets stored as this attribute set that also goes with the object. And the thing to notice is that, of course, even a very small object, an object that consists of a single body chunk, will then always have two allocations. And for a cache of very small objects, that brings with it a lot of alignment overhead that is lost because we had to make two allocations for the single object. If one is caching extremely small objects, then that overhead can become quite significant. So in the new model, we have made the object space linear with the attributes just what happens to be at the very start of this linear space, and the body what comes after it, and then optionally there could be even more bits or pieces if one is using ESI, for example, that also would fit into this this picture in the same linear space. So the small objects then become a single chunk of only one allocation, and also the larger objects have saved an allocation in this new model. And then coming back to what happens in terms of partial objects. So this is a new concept with MSE version 3, and that is that objects are not either in system memory or not in system memory. They may be partially in system memory. And this becomes important for the very large objects. The video file, like your traditional very large file of video, and your viewers only watch the first 10 seconds of it and then break off because they didn't find it interesting. The new model allows us to keep the chunks that make up the body individually, and the chunks may be removed from system memory. They are on disk in this setup, but they may be removed from system memory in order to not take up the valuable space there if they are actually not accessed. So the chunks are individually LRU'd, or least recently used. So we keep a least recently used list that consists of the individual chunks that make up the bodies. So even though someone was only looking at the very first 10 seconds of that video file, the rest of that video file would never be accessed. And as new system memory was needed because of traffic happening on other objects, those would then be removed individually, while still keeping the very first 10 seconds of the video without any problems. And we do not waste system memory space on this very large object, not when only part of it is actually being referenced. And of course, once someone actually wanted to watch the whole video file, then it will be observed that we lack content. And that's when the new chunk of the object is inserted and then filled from disk. And once it is filled, of course, then the delivery thread of that client request is able to continue and deliver more content to that client. This also works with range requests, so if there are range requests coming in and they ask for specific parts of that object, then it's only those parts that are being actively referenced that are being kept in memory. So over time, it is very possible to have a scenario like shown here, where there are holes in the middle of the object that is not in system memory. The whole object is on disk, but only the parts that are being used are kept in memory. This would also be the case for the scenario where maybe a large ISO file and you have a very slow client, and instead of keeping all of that ISO file in memory while the client downloads it piece by piece by piece, as the client delivers one part of the object, then that part is no longer referenced, and it might be removed from memory because it was needed elsewhere. And that is also completely fine from this setup point of view, and we save on the memory usage. And an object not being referenced at all will be able to have all of its constituent parts removed from memory after it has been asked for from other sources, and these parts is what happens to be at the very head of the least recently used list and are removed. So once an object is completely not accessed, it will over time be also not take any space in system memory. Right, so some words about how to use this from an administration point of view. So we have this configuration broken down into a sort of hierarchy, and of course when one is configuring and setting up a very large cache. There are multiple disks involved, and there are decisions to be made about where to store the metadata and how the whole thing should fit together, and how to express that to Varnish as a configuration at startup. And previous versions were a bit lackluster in this area, creating some steps that was unnecessarily complex. We have tried to improve on this, and we've done that by making the whole configuration hierarchical. That's a very hard word to say. At the very top, you have the environment. That is where all of the objects in memory actually reside, and where you configure how much memory to use. One step below, there is the book, and the book is where you configure where the metadata of your stores should be stored. And we have made this into a separate configuration to allow for the setups where you'd like to use spindle disks. If configuring a cache with spindle disks, it will be very beneficial to be able to take at least the metadata, which is much smaller, and put that on solid state drives. So the book is then configured separately from the stores, but they may, if you so choose, of course, lay on the same devices. And then at the very bottom of the hierarchy, there are the stores. That is the actual payload data for the cached objects. And in the new setup, this then comes down to a configuration file. Where this hierarchy is expressed, and you can then create your configuration to model specifically what types of devices and the sizes that you'd like to set up. And then once the configuration is done, we still have this initialization step in order to prepare the files and create all the data structures and such. It goes much faster than before, so it's quite an efficient step, but we still require that there is a specific utility that is used in order to set this up, instead of Varnish just doing the stuff upon startup. This helps not go into any problematic scenarios where you mistakenly overwrote your cache by accident upon starting the Varnish binary. And then to the configuration or initialization utility, you just pass the configuration file, and likewise, when you start the Varnish binary, the very same configuration file, it may be propagated automatically by setup scripts or something to your servers, and there are no specific separational steps. That was a bit cumbersome in the previous version. And then for the Varnish daemon, you just specify specifically the type of stevedore, MSE3 in this example here, and then give it the configuration file previously prepared. Next topic, counters, in order to get some views inside of the box of what is happening. And specifically, I'd like to point out some of the new disk counters and what is happening in terms of AIO and your IO performance. So we have a whole set of new counters here that shows exactly what the system is doing at any point in time. You will have your lists of the IO operations that are currently underway, broken down into read and write operations, and then you will have the same again for the total size that those operations that are under way at the moment. The total size of the vectors OIO that are queued with the kernel for execution by the drives. So that shows what the system is doing at the very moment. And then you have the accumulative counters. Those are the ones that starts with a C underscore there. That shows how the system has been performing over the time since the Varnish daemon was last restarted. And you will see also that there is this queued counter here. So if the amount of I/O is starting to exceed what the disks are able to execute, then you reach this plateau where it doesn't help to start giving more tasks to the kernel for performance for execution by the disks, and we start queuing the threads instead, and that also shows up explicitly in the Varnish stat counters, and you will be able to observe this and also take action if necessary. Very last counter there, the write queue overflow, is a sort of interesting aspect as well. And this is configurable, but once you reach the limit where your disks actually can't take any more added data and you start lagging behind, one of the choices that might be the right one for you in that case is to actually then stop storing to disk and instead treat the cache as a pure memory cache. And we have that option also in the new architecture, and of course these will still be cached objects. We just don't store them to the disk in order to not lag behind, and as long as this content is hot and in the cache, we will continue doing cache hits on it. But once it goes out of the cache, then it would have to be a cache miss and go to the backend at some future point where there might be less write activity happening, and we might persist the object at that point in time. On the user space page cache side, there are some other counters as well. I'm not going to go into them into the first ones in much detail, but you will see that they mimic very closely what you are used to see from the regular vanilla malloc stevedore. But the very last two ones are interesting, and this shows how the middle fast system memory cache of yours is performing. So it will show how much data is being served from system memory and how much data is needed to be read from disk. So the mem cache miss in this case, that is misses for the system memory cache, but not misses that goes to the backend. These are misses that goes to the disk on the Varnish server instead for reading there. Right, availability. We are getting close to releasing this. The product itself is feature complete, and we are in internal testing, doing benchmarks and stress testing and fuzzy testing, and yeah, lots of steps there. And also preparing for enabling some external testers, that is our customers, to be able to test with the new version. The product itself will be released for Varnish Cache Plus 6.0, which is the new version of Varnish Cache Plus. That is also close to release these days. And that takes us into the questions section. Yeah, so the first question here is from Chris Aurelio. He's asking, do the MSE3 memory sizes in the configs needs to be aggregated for a sort of memory total, or does the top level of the hierarchical model represent the hard ceiling for memory usage? That top, the memory usage and what one would want to configure there mimics very closely what you would do for the malloc type of stevedore. And what that means is that it is a calculated upper limit of object payload data that we allow to be kept in memory. So the system is going to continue doing malloc calls for the system allocator up until we reach that level, and then make sure that it does free calls for the amount necessary before the new allocations are done. So what that doesn't take into account is any other type of overhead, and there are other types of overhead in terms of all the threads that you configure Varnish to use, and the workspaces those threads use as part of the HTTP handling and such. So it is the same as for the malloc stevedore in that those overheads are not taken into account, and you would need to make provisions for that in the sizing. This is something we have some plans to look at in the future, but it will not be in the first iteration. Next question from Carlos. No reason to use multiple stevedores in MSE3 for multi-disk setups, right? Single config with multiple disks seems better, simpler, less state, etc. Yes, that is correct, Carlos. So in the new setup with the configuration file, it will be natural to say that each disk is a separate store, for example, in the configuration file. And then you pass the single configuration file that mentions all of your disks to Varnish, and it will then distribute the objects between the disks automatically. A single object will always reside on a single store or a disk in that configuration, but it will distribute them out so that all of the disks are used. Next one from Matt Levine. Does MSE3 use the same LRU algorithm from MSE2, least frequently used? Not at this point. It is using a strict least recently used. We might look into some tunings on that in the future, but it will have to be evidence-based. In MSE2, we had this change to the LRU mechanism, and we are still evaluating whether that should be taken forward or not. But when it comes to the reason we had the specific least frequently used mechanism in MSE2, it was mainly as a basis for doing the defragmentation algorithm, so that we could keep paint a bit broader picture than a single, this is the least recently used object for deletion, but you would then paint a larger part of the cache, and then you can use that information in order to remove the objects that are aligned closely by in the address space, so that you can create continuous free regions. So yeah, a bit of complexity in there, and there is a similar but not exactly the same mechanism in MSE3 to deal with fragmentation. And question from Alexei, would MSE3 support dynamic storage backend allocation deallocation, yeah, extending physical disk storage and extending it in Varnish without restart, since you have middle tier and can work without real disks? This is something we have been thinking about a lot, and it has been very much in the mindset during development and design phases. So this is an area that we want to address. But in the very first release of the new architecture, there is little support for it. There is some as an offline support where you can add and or remove books together with the stores that use that book as a metadata store. So at the second level of the hierarchy, it is possible to add and or remove setups, but you would need to restart Varnish to make use of it. But of course it's persisted, so the objects would be there upon restart, but you cannot do it online. Right, so that is also the very last question. So I think I'm going to say thank you all big time for participating in this, and I hope you enjoyed and found it useful. And until next time, goodbye.